I would like to start with by correcting something I omitted yesterday. So in the separatrix theorem, I forgot one hypothesis, and it was that the curve involved in the statement is a tree. So I'd like to thank Olivier and Fabio for pointing that out. And we also almost discussed a counterexample with cycles of curves. So okay, this was just to make it up for my mistake of yesterday, and today I would like to talk about foliations on X with non-pseudo-effective canonical bundle. So there is a theorem by Miyaoka, and the theorem states that if we take f on X, and here we are not necessarily reduced, and there exists an ample divisor with intersection product with the canonical of f negative, then the leaves of f are rational curves. So we can find a birational map, and a fibration such that the general fiber of f is rational, and f tilde, the foliation induced on X tilde by f, is f, so the fibration. So maybe the first thing to prove is that rational fibrations satisfy this. So if we consider f rational fibration, then the canonical of the induced foliation is the relative canonical bundle, as we've seen, plus some correction term.
You mean the general fiber of f is multi-rational, just in the statement of the theorem? Is multi-rational fiber or just rational?
Thanks. Thank you. No, X is a surface. X is a surface. We are throughout. If I forget to say it explicitly, X is always a surface. There will be in 5 minutes the first and the last threefold of these lectures, but then it's okay. So the canonical bundle of the induced foliation is the relative canonical bundle minus some correction term contained in fibers, supported maybe. In fibers of F. And so let's take F, a general fiber. So then KF dot F well, the intersection with this thing is 0. The intersection with the pullback of the canonical of C is 0. So this is Kx intersected with F. That's -2. And now F is an F divisor. And then, well, let's say for all natural number and for all A ample divisor, NF plus A is ample. And then KF, let's call this H. And the intersection of KF and H, it's -2n plus A times KF. So if n is very, very big, this becomes negative. So it satisfies the hypothesis of the theorem. OK? Well, let's get to the proof. And once again, I will mismatch the statement and the authors of the proof. This is a proof by Bogomolov and McQuillan. So H is ample. Then I can find big enough n and an element in the linear system of n times H with the following properties. C is smooth, and C avoids all the singularities of F. OK, this is just Bertini theorem. Now I will construct an auxiliary foliation. We will consider the threefold.
I have a question to remind me. What would be the easiest example where there is a vibration?
Yes.
Negativity does not hold for any output.
But the negative, so a vibration, a rational vibration, and an ample divisor with a non-negative intersection. So maybe if you take Hilbert surfaces, you can already find one. Maybe we can discuss later, but yes, I have to think about it. So we take this threefold, and on Y, we put the foliation of rank 1, which is F on every slice. So, OK. So this is X. And here we have C. And the cube is Y. And here we have C again.
The condition there is that C intersected with singularities is empty?
Ah, thanks. Oops. Yes. Yeah. I said it orally, and then I forgot the C avoids all the singularities of F. Thanks. Yeah. OK, so this is C times C, and in here we will take the diagonal. and I will call it D. So D is the set of pairs C, C with C and C. Okay. So once again, the intersection with the singularities of D is empty. And through every point of D, so there is a smooth, let's say, it's not a leaf, but it's an analytic neighborhood centered in D, contained in a leaf. And well, let's say that U is a tubular neighborhood of D in X, and we set V as U intersected with, let's say, local leaves of G passing through D. Okay, so V is an analytic surface. V is an analytic surface, and we consider the normal bundle of D in V. This is the restriction of the tangent of G to D. So the direction, it's almost tautologically the direction of the foliation G tangent to D is exactly the normal direction to D in V. But this is isomorphic to the restriction of the tangent bundle of F to C. So by computing degrees, so we pass to degrees. We pass to degrees, and here, so remember that C was in a linear system of multiples of H. So this is positive. Okay? So this normal bundle is ample. So this normal bundle is ample, and by the theorem you've seen in the first lecture, proved by Jean-Benoît Bost, the surface V is algebraic. And we will call S the Zariski closure of V. So why did I do all these? We just proved that the leaves of F are algebraic. So those are algebraic if and only if the leaves of G are algebraic. So this nice construction is a way of separating the leaves of F passing through C. but they are basically the same. So those ones are algebraic, if and only if those ones are algebraic, and we just proved well. The leaf of G through the point CC in D is contained in S intersection the fiber X cross C. So it's algebraic. Okay, so now, is this okay so far? So now, why are they rational? We have, oops. We have a fibration from S to C, and we have a divisor D in S, which is, well, almost ample. D squared is positive, and G, let's say, near D coincides with phi. Okay, now we consider our phi as a foliation. Let me write it like this. It has reduced fibers. So its canonical is the relative canonical bundle. And now we have surface theory coming to help us. There is a theorem called Fujita semipositivity, or Arakelov theorem, which says that if the genus of the fiber, this was not a smart idea. If the genus of the general fiber is at least 1, then this relative canonical bundle is an F divisor plus an effective. So it cannot have negative intersection with D. So the fibers must be irrational. Okay, so that's it. That's the end of the proof. Well, maybe just to conclude, one thing can take tilde to x as the reduction of singularities. And that's it. So we have a pretty precise idea of what happens when the canonical of the foliation is not pseudo-effective. So we go back to the pseudo-effective case. So we go back to kf of f and f reduced. Okay, so we've seen yesterday that pseudo-effective divisors have Zariski decompositions. And we can define with the Zariski decomposition something called numerical Kodaira dimension. We say that this is 0 if P, this positive part, is numerically equivalent to 0. So this means that the intersection of P with every curve is 0. We say that the numerical Kodaira dimension is 1 if P is not numerically 0, but P squared is 0. And we say that it is 2 if P squared is positive. So those are the only 3 possibilities which can happen. And so the first remark, or lemma, let's say, is that nu of f is a birational invariant. So just recall that here f is reduced. So how does this work? Well, take a birational morphism. Well, let's take a birational map. And we take resolution of the indeterminacy. So let's say that f induces G on Y, and we call, well, f tilde the induced foliation on W. So it is sufficient to prove that the numerical Kodaira dimension of f tilde is equal to the numerical Kodaira dimension of f, and that this is the numerical Kodaira dimension of G. So in other words, it's enough to prove the statement for a morphism, not necessarily for a rational map. So we can assume mu is a morphism. So we have mu and morphism. And, or maybe I'll use this more suggestive notation. And here we have F tilde and F. And F tilde is the induced foliation by F. And so the first, I will tell you what the ingredients are, and then I'll leave you to fill the details. So the first thing to use is that the canonical of F tilde is the pullback of the canonical of F plus an effective divisor, an effective and mu exceptional divisor. And then, so first step, if P plus N is the Zariski decomposition of Kf, then the Zariski decomposition of Kf tilde is the pullback of P as positive part plus the sum of the pullback of N plus E as negative part. And then the second step is just to conclude. Ah, yes, thanks. Thank you. And then, so let's do conclude. And the main thing to use is the projection formula. So if you have L on X and C on X tilde, then this intersection product equals this intersection product. So the projection formula has to be used here and also here. Okay? It's not difficult, and I think it's a nice exercise. The first one, to understand a little more the Zariski decomposition. Okay. And now I would like to talk about a special, well, one of these cases, the case of numerical codire dimension 0. And so the theorem here is that if we take F reduced and relatively minimal, with numerical codire dimension 0, then, well, I'll tell you what the slogan is. Modulo a finite covering F is generated by a global vector field. But now I'll tell you the precise statement. So there is, let me use the same notation. We can find, well, F X surface always. There is pi generically finite and P birational. P from Y to Z. So we have F here. We have an F tilde induced here, maybe G. And we have H here. So we can find pi and P such that H is generated by a global vector field. OK, so maybe first of all, some comments. First comment, what does it mean in terms of the canonical of the foliation to be generated by a global vector field? So foliation generated by a global vector field is corresponding to global vector field, global section of the tangent bundle. And well, maybe this is a little pedantic, but Tx is isomorphic to Tx tensor OX. So canonical of the foliation is trivial in this case. And the second, well, maybe the most important comment, why is the result interesting? Because foliations generated by global vector fields are classified. So the theorem gives you a complete understanding of this case. Everything is smooth. So I'm assuming generically finite, so I can take a resolution. Yes. So yeah, here there will be a ramified covering, a desingularization, and this is the relatively minimal model. So yeah, maybe I can add it here. Y and Z are smooth. Thanks. OK, so this gives me, I will tell you what the classification is, and this gives me the opportunity to make some other examples. So what are the classes of foliations generated by global vector fields? We have Kronecker foliations. On abelian surfaces. So an example is, well, let's take an easy abelian surface. And F given by this distribution of hyperplanes So let's pretend that, that we are not in complex dimension 2, but in real dimension 2. So I'll draw the torus with the two identifications. And these hyperplanes project onto X. And well, let's take hyperplane through 0. And it gives us a curve in X. And well, this leaf closes up, so the leaves are algebraic. If and only if lambda is a rational number. So if lambda is a rational number, the leaf is an elliptic curve, and otherwise it will fill densely the surface. Okay. So this is one example. 2.
So lambda is fixed now. F is a foliation.
Well, maybe I should. Yeah. So this is a family with a parameter. Okay. So the second example is quasi-elliptic fiber bundles. And the easy example is we take E an elliptic curve and C any curve. And we take the projection onto C. And there are other two families, and one is a suspension of representations of a representation of the morphism of an elliptic curve. To P1, oh, sorry, what am I writing? Sorry, there was something wrong here. P1 of an elliptic curve, the P1 of, the pi1 of P1 is not very interesting. Okay, I hope you've seen some examples of those last week. And then generated by so on X, P1 cross P1, and F generated by V1 times V2, where Vi are vector fields on P1. Okay, those are the four families. And now I'll prove the theorem, but before proving the theorem, I want to do a very easy work, which will be fundamental proof. And the very easy remark is the following. If we have a divisor, which is at the same time numerically 0 and effective, then D is really equal to 0. Okay? This is probably one of the main ingredients of the proof, and that's because if D is not 0, then we can, well, maybe for any ample divisor, H will have positive degree on the non-zero component of D. So D cannot be, so indeed. Okay, so D cannot be numerically 0. Okay, now. So, for the proof, first step we will prove is that if KF has a global section, then KF is trivial. So let's assume we have a global section here. Then, well, I told you that KF and P have the same global sections. So if we take the 0 locus, this D plus N, where D is effective and numerically equivalent to P, which is numerically equivalent to 0. Therefore, D is 0 by the precious remark. And now, we get that the 0 locus of S equals N. But yesterday, the last theorem we proved said that when F is relatively minimal, the divisor N has an expression like this with all the BI's strictly less than 1. So, and this is an integral divisor. So N is 0, and S is a nowhere vanishing global section. So this gives an isomorphism of KF with the trivial line bundle. Okay? So step 1 is done. Step 2. I'm going to prove that, well, we can find the power of KF. Some power of KF has sections. And here again, we'll do some cases. So 2 cases. We'll consider either VH1 of X is 0 or it's not 0. Okay. So maybe I'll open a small parenthesis here. Just another small digression. What does this H1 represent? So we have a short exact sequence like this. And we pass to cohomology. And at some point, we have the H1s. And the H2. And this is the Picard group. Maybe there is Z here. This is the Picard group. And this arrow is one that to a line bundle, and is an isomorphism class of a line bundle, associates its first Chern class. And the first Chern class is 0 if and only if, sorry, C1 of L is 0 if and only if the intersection product of L with C is 0 for every curve. So the H1 of OX is the, let me write a sentence, is the numerically 0 line bundles or divisors. Okay, so this is the end of small story. So what does it mean for the H1 to be 0? It means that if we have D, an integral divisor, which is numerically 0. Yes?
C1 of L is a torsion. Because you're in S2 of in integral homology. So you might
Because I took Z. You're right.
But it's not a big deal, it's just...
No. Thanks. No, thanks. So, but maybe this helps here. If D is an integral divisor, then there exists N such that this power is trivial and, well, multiple of N is 0. Is linearly 0. Okay, this is just to say that we do have a numerically 0 divisor. We take this hypothesis, so P is numerically 0, it's a Q divisor. And then we take N, so by this discussion, there exists N such that NP is linearly equivalent to 0. And then NKF, or this is NP plus NN, sorry. This is linearly equivalent to NN, and that's effective. So we found a global section of KF. In this case, if the H1 is trivial. What happens if the H1 is not trivial? So again, here we will use some results from complex geometry, or some constructions. I will tell you in a second. What are the facts? First, there is a Hodge duality. The dimension, I will state this weaker form, the dimension of AH1 is the same as the dimension of global sections of the cotangent bundle. So we have non-zero global one forms. And the second thing I will use is the Albinism Morphism. The Albinism Morphism is a morphism that goes from the variety x to the functionals on one forms modulo classes of loops in x. And what is this functional? So what is this morphism? We fix an x0 in x from the start. And it goes to the integral from x0 to x along any path, because we are taking this quotient of one forms. So we're going to use these two things. And again, there are two cases. So, OK, so there is a non-zero global one form. And so omega is a global section of omega 1. And again, so first case, assume that there is such omega such that the restriction of omega to f is not identically 0. So we consider omega. And then we consider the dual definition of foliations. This is a quotient of, so this is omega. And it is given by definition of f. And here we have an immersion in kf. So this hypothesis is equivalent to saying that alpha is non-zero. But so alpha is a global section of kf again. So this is what we wanted in this first case. And so what is the other case? The other case is that for all global sections, the restriction is 0. And in this case, so in this case, I want to prove that f coincides with the Albanese fibration. An important thing I forgot to say. I'll try to add it. Which one was it? No. So an important property of the Albinism morphism is that if H0 is not 0, then the morphism is not constant. It's really important. We will use it in a second, and so we want to prove that F coincides with the Albinism morphism. So how do we do this? Well, we have our X. And let me, and this is supposed to be F. And there I fix a point x0 in here. And I want to prove that if y and z belong to the same leaf, of F, then they go to the same point. So I have my y and z here. And when I do my integrals of forms along paths, I can choose the path I want. So I will choose a path from z to x0. Any. And gamma 2, we will take, gamma, composed gamma 1, where gamma is contained in the leaf. I can do this at least for two very close points in the same leaf. But so it's easy to see that then for all 1,4, the integral from x0 to y, or this 0 to z, and then from z to y, and this is 0. Because, so why is this 0? Because we chose gamma inside the leaf, and omega is 0 on the leaf. So they go to the same functional. Okay, but then now Alb is non-constant, and we just proved that it has non-trivial fibers. It's not generically finite. Then it is a fibration, and the leaves of F are contained in fibers. Okay, let's go back to, is that okay so far? So we reduced ourselves to this second case where there are global one forms, but all of those vanish along the foliation. And we proved that the leaves of the foliations are contained in these Albanese, in the fibers of the Albanese map. And well, these fibers are not everything by this very important property I wrote there. And the map is not generically finite because we just found one-dimensional disks in the fibers. So we have this, and we go back to our Zariski decomposition of KF. And yesterday I proved that N is F invariant. I proved that N is F invariant. So if we consider F general fiber of Alb, then okay, then the intersection product of KF and F and the fiber is P times F plus N times F. But then N being F invariant means that the support of N is contained in fibers of the Albanese map. So this is 0. General fiber doesn't meet something contained in other fibers. I can move it around. And P is numerically 0, so this is 0 again. OK. But, well, we said that our foliation is indeed a fibration. So this on the other side is to the genus of F minus 2. So F is an elliptic curve. And again, using some surface theory. Then F and also the Albanese map are elliptic, is an elliptic fibration. And using some surface theory, or more precisely something called the Kodaira canonical bundle formula. I will not tell you any details about this. But, well, if you want to ask questions later, I'm happy to answer. Using this thing, we can prove much more. We can prove that F is isotrivial. And isotriviality for elliptic fibrations means something very strong. So let me call C the base of the fibration. Isotriviality for elliptic fibrations means that there exists a finite base change. Such that, here we take the main component of the fiber product. We take the singularization And this desingularization is birational to a product. So isotrivial elliptic fibrations are products modulo finite phase change.
This is not Serrano theorem in general. Why for elliptic vibration? There is more for elliptic vibrations.
Or maybe you're right. I don't know. I have in mind the
No, this is
the periods.
This is true for any.
Yeah, for genus at least one.
Serrano's theorem.
For any of genus at least one.
Yeah.
Yeah. Yeah. You're right. I have in mind the moduli map. That's why I write it like this. But yeah, thanks, for sure. OK. So not only we proved that a multiple, well, not only we proved that KF has a global section in this case, I think we proved the whole statement. So we proved the theorem in this special case. So this is our generically finite map. This is the birational one. And this is the quasi-elliptic fiber bundle. OK. So we are left with our last step, which is how to go from having global section of the multiple of KF to global section of, well, I don't know, some canonical bundle of some foliation on a related variety. So this is done with covering, with cyclic coverings. So let me tell you how they work. We have L on X, a line bundle. And we assume that some power of L has a global section. OK. And we consider a point in the smooth locus of E. So around this point, E is the zero locus of a variable. Well, and now I want to consider, I want to do this right. Yes. I want to consider L to the power n as a three-dimensional manifold. Sorry, it's L, not L to the power. I want to consider the fiber bundle L as a three-dimensional non-compact manifold. So this is L. In here we have the X as a zero section. And no, you're right. Sorry. I'm getting confused. I want to consider L to the power n as a three-dimensional manifold. And here I have the global section given by E. S, So S equal to 0 is E. And I call Y the variable on a fiber. And here we have our x0 somewhere. So there are not enough dimensions to draw this well. And inside L to the power n, we consider the closed subvariety given by the equation y to the n minus 6 is equal to 0. So sorry. So the restriction of the map from L to the n to x gives a finite map from y to x. So let me call, I don't know, pi. Pi locally. We define y just locally. Yes, yeah, you're right, but well, yes, but I called the local chord, yeah, maybe I gave two names to the same thing.
Yeah.
Maybe one is the pullback.
Yeah, exactly.
So,
anyway, x equals 0 must mean s equals 0. I mean,
yes,
yeah.
so around the smooth point of E, S can be taken as a local coordinate.
But I think you were right the first time. It should be inside L. Right?
Itself, yeah, sorry, I'm getting a little confused. Thanks. Yeah. No? Okay. So, so let me write it like this. All these local definitions of y glue and the restriction of pi to y is finite of degree n. And well, now there are some singularities involved. Y is singular over the singular locus of E. But I don't want to get into the singularities. We will pretend that, that everything is smooth, even though it clearly isn't in our situation. But I think it's easier this way. And there is another important property. If we push down the structure sheaf of Y, this is finite sum of is the direct sum of powers of L. And now we want to apply this construction to L equal KF. So we will take n the smallest such that kf to the k has global sections, and E is n. And there is yet another thing that I will not prove. So we can construct y to x cyclic covering. And we get a foliation G on y. And the covering pi ramifies along the support of n. So the thing I will not prove is that since this is F invariant, the canonical of G is the pullback of the canonical of F. And so this can be proved with local one, with taking the one form point of view. Okay. Okay. Let's see if we did this well. So the global sections of the canonical of G so these are well, the canonical of G is the pullback of the canonical of K, of F. And this is, well, I'll do another step. Of course, tensoring by OY doesn't change anything. And then we use the projection formula. And we use the projection formula and the fact about the push forward of the structure sheaf. Okay, so let's look at the, okay, and then we can, sorry, I'm really being very, very pedantic here. So this is 1 minus j. So now this is non-zero because there is at least one summand which is non-zero, the one corresponding to j equal to 1. So we have the h0 of x KF. And then the following one is the H0 of X OX. And then there is maybe other stuff, but this is C. So that guy is non-zero, and we are done. Okay, and now, well, now once again we can prove that the Zariski decomposition of G is the pullback of P plus the pullback of N. So the numerical Kodaira dimension of G is 0, but maybe we lost G being relatively minimal. So we can find a relatively minimal model. This is our P. Z and H are relatively minimal model. And sorry, C. And KH has a global section.
This Y may be singular. This Y may be singular.
This Y is singular, and admittedly, I'm cheating here, so I'm not. I'm not dealing with the singularization, but I think, okay, so where can I, so, okay, Y is singular, and of course, Y is singular here, but we will pretend for simplicity that Y is smooth. And I think using the structure theorem about N, one can prove that Y is smooth, but the singularities are not that bad, and so this doesn't affect this birational invariance, because this is the point. If the exceptional divisor is effective, then everything works well. But we didn't say anything about the singular case, and I will not. Okay. Okay, but now by step one. KH is trivial, and then KH is generated by a global vector field. Okay, and that's it. And so corollary of the proof. Corollary of the proof is that if the numerical Kodaira dimension of F is 0, then well, there exists always a natural number such that multiple of KF has a global section, and we will give another name tomorrow to this property. But this is for today.